I correct?
Why, hello. Today we're going to go on to section 17.4 that deals with Green's theorem. But before we do that, I want to make one comment of a mistake that I made the other day. We had a definition of a region being connected, and that was a very simple definition. If you had a region, it was connected as if you took any 2 points in the region, you could find a path connecting the one point to the other point. That was not a problem. Okay, that definition, we put it correctly. The definition of simply connected should read that a region is simply connected if it is connected and every simple closed curve in the region will have its interior also in the region. Okay, now in today's lecture that's not all that important, but it will crop up later on. So the one problem where if we had all reals x, y such that x did not equal 0. So it's the whole xy plane except we're not including the x-axis. Now if I take any simple closed curve that's in that region, its interior will be in the region. But this region's not connected, because if I take a point here and a point here, there's no path that I can get from here to here and have that path be entirely in the region, because if I do, there's always going to be a hole right there where I'm not in the region. So this is not, since it's not connected, it's not even a candidate for simply connected. You must be connected to be talking about using the adjective simply connected. Now today we're going to do one of my very favorite theorems. It's Green's theorem. But before we do it, we have to understand what do we mean by positive orientation. Positive orientation. You only talk about orientation when you're talking about a closed curve. And if you have a simple closed curve, remember simple means it just does not intersect itself. This curve right here is not simple because it's intersecting itself. That's not simple. But a simple closed means it starts and ends at the exact same spot. We say it has positive orientation if you're going around it in a counterclockwise direction and you go around just one time. So if I start here, I'd have to go in a counterclockwise direction, and that's called positive orientation. And you use that concept, you know, when you were talking about angles being positively oriented when they were in standard position. When you measured an angle this way, we considered that the positive rotation. So it's the same thing. But you've got to be going in a counterclockwise direction. The way I look at it is if I have a little guy and he's walking around the curve always has to be to his left. I prefer that direction, that definition myself. If I have a little guy walking along the curve, his left arm is always pointing into the region. Now, why do I mention that? Well, because when we get to talking about orientation when we're in space, counterclockwise won't necessarily make sense. Where walking around with a little positive K on top of your hat would make sense with having the region inside. All right, now, this is Green's theorem. And we should have the word Green's theorem up at the top and give him credit. Green's theorem. Let C be a positively oriented, piecewise smooth, simple closed curve in the plane, and let D be the region bounded by C. If P and Q have continuous partial derivatives on an open region that contains D, then we should have a little circle around here because it's the integral along the closed curve of C of P dx plus Q dy is equal to the integral over D of the partial of Q with respect to x minus the partial of P with respect to y over the region. Notice what they're doing here. You have a simple closed curve. Okay, there's your curve C. Your D is the interior of this region. D is the interior along with the edge. All right? Now, first of all, C, you have to have positive orientation. So we're doing our line integral around C in a counterclockwise direction, like that. And we're saying if I integrate along the curve of P dx plus Q dy, I will get the exact same answer as if I do an area integral, a double integral, over the interior region of the partial of q with respect to x minus the partial of p with respect to y, dA. And I use dA because we could use dx dy, but you know, if the region just cries out for polar, we'll use an r d theta. I'm not going to do the proof of this, but the proof, a partial proof is in your textbook. A complete proof is really an advanced calculus topic. So, you know, if any of you got on to advanced calculus, you'll actually see a much formal proof. But they have a nice little proof for just a special case, all right, of a simple closed curve. This is really a cool theorem if you look at it, because sometimes doing that integral, and notice it says it's piecewise smooth. So it's okay to have a couple sharp edges, but if you can break it up into smooth pieces, but a finite sum of those, then it's called a piecewise smooth curve. So using this, let's apply it to this problem here. Evaluate the integral of x to the fourth dx plus xy dy, where C is the triangular curve consisting of the line segments from, now notice they're giving me orientation, because remember, when I apply Green's theorem, this integral along this curve is equal to the integral over this region if I'm going in a counterclockwise direction. Or if I have my little guy walking along the edge, as he walks in that direction, his left arm is always pointing into the region, which we will be using a little bit later today. All right, so let's just draw a picture of what our region looks like. Okay, our region's going from, our curve is going from 0, 0, so here's 0, 0, to the point 1, 0. So I'm going in that direction. And then from 1, 0 up here to 0, 1. So we have that line segment going this way. And then we're going from 0, 1 back to 0, 0. So this is the curve. This is the curve C. Notice C is not smooth. It has a couple sharp edges, but it's piecewise smooth because this is smooth, and that's smooth. And notice this is my interior. That's my D. That's represented by, that's the interior of that curve. So now using Green's theorem, notice what Green's theorem says. It said the integral over the curve with positive orientation, notice I am going counterclockwise, of p dx plus q dy is equal to, now notice we're saying that all of your partials have to be continuous. Well, geez, these are polynomials, so they have infinitely many partial derivatives. That says this is equal to the integral over the region of the partial of q with respect to x minus the partial of p with respect to y dA. All right, so notice this is my p right here, and this is my q right there, because it's p dx plus q dy. And notice what this little circle here means. When you put a little circle on your integral, you wonder, why does she put that sometimes? That's when you're integrating over a closed curve. When the curve that you're integrating around starts and stops at the same spot. Okay? All right, now let's look at this. Applying this, let's see what we got here. The partial of q, here q notice is xy. So the partial of q with respect to x is just going to be y. All right. In addition, p is x to the fourth. So the partial of p with respect to y is going to be 0. Okay, so filling that in here, what's the partial of q with respect to x? It's y. What's the partial of p with respect to y? It's 0. And I'm integrating over this region. I'm thinking I'll do a dy dx. Now I have to figure out what my limits of integration are. Well, first of all, let's see. This curve right here, I'm going to put it in the form of y equals mx plus b, if that's okay with you people. Its slope, if going from this point to this point, you're going down 1 to the right 1, so that's a slope of -1. And your y-intercept is 1. So the equation of that line is y equals minus x plus b. If I take an arbitrary point in the x-axis and I ask what's y ranging from, it's going from 0 to minus x plus 1. And then if I sum those all up, my x's are going from 0 to 1. And so I have changed, with the aid of Green's theorem, I have, instead of doing a line integral along that curve, that closed curve, I'm doing an area integral. Now notice, we could have done the line integral, but you would have had to do 3 separate integrals. You with me? Because there's no one definition. You have one definition for this guy, one definition for that piece, and one definition for this piece. And I guess we'll finish this. If I do the inner integral, instead of writing minus x plus 1, I'll write this as 1 minus x of y dy. That's going to give me 1/2 y squared. And we're going from y equals 0 to y equals 1 minus x, which gives me 1/2 1 minus x squared. And if I take that and do my outer integral, it was 1/2 1 minus x quantity squared dx, and we're going from 0 to 1. You could multiply it out if you want. I guess that's what I'll do. I get 1 minus 2x plus x squared dx as x goes from 0 to 1. So we get 1/2 x minus x squared plus 1/3 x cubed. And we're going from 0 to 1. Well, if you pop in the 1, you're going to have 1 minus 1 plus 1/3. Pop in 0, you'll just get 0. So I have 1/2 times 1/3, which is 1/6. Okay, not hard. Notice, each time you must make sure that you have continuous partials on the open region that contains D. So you have to look at your partials and make sure that they're defined continuously all over that region, not just along the curve, also in the region. Okay, let's look at another one. Next one. Evaluate the integral along the curve of 3y minus e to the sine x dx plus 7x plus the square root of y to the 4th plus 1 dy. This is a hideous. To do this as a line integral, we'd have to get a parametric representation, right? We would have to get a parametric representation for this circle. X equals 3 cosine t, y equals 3 sine t. Then you'd have to substitute for x and y for those, for dx, for dy. It would be a pretty messy integral. I mean, it would be a lot of work. Instead, we say the integral over the curve of p dx plus q dy is equal to the integral over the region, partial of q with respect to x minus partial of p with respect to y, and then we'll just say dA. So in this particular case, let's see, my p, this is my p. P is 3y minus e to the sine x. So the partial of p with respect to y is just 3, because that's 0. And my q is this ungodly 7x plus y to the 4th plus 1 to the 1/2. Partial of q with respect to x is just 7. So plugging that in to here, we're going to have the integral over d of partial of q with respect to x, I got to be 7. Partial p with respect to y, I got to be 3 dA. Now what was my region? My region was the circle that's bounded by x squared plus y squared equals 9. What is that? Circle of radius 3. Now, to me, a good mathematician is a lazy mathematician. This is equal to 4 over the double integral over d of dA. When your integrand is 1, what does this integral turn out to be? The area of the region. So this is equal to 4 times the area of the region. Well, people, I know how to find the area of a circle. What's the area of a circle? Last time I looked, the area of a circle is pi r squared, right? The area of that circle is just pi r squared, and since the radius was 3, it'd be pi times 3 squared, or 9 pi. So this is just going to be 4 times 9 pi, which is 36 pi. A good mathematician's a lazy mathematician. I mean, we could have set up a parametric representation. We could have done it in polars, but why? Right? If I know what the area of a circle is, I'll do it that way. Now, granted, if you do it on the test the long way, you know, you won't lose points. Okay, I'll just say, oh, you made your life difficult. Okay, now this one I want to do it both ways. It says evaluate the line integral by 2 methods. And you have to do this in the first couple of problems in your homework. We want to do it directly by doing the line integral, and then we want to do it using Green's theorem. And we hope and pray we get the same answer for both. All right, so the first one that I want to do here is the region that I'm integrating over is the circle that has center at the origin, and the radius is 0. I'm going to have to get rid of this red pen. Let me put it over here so I will throw it out and not pick it up again. Okay, so here's my circle of radius 1. All right, and I want to do it as a line integral. So we have to come up, when you do a line integral, you must have a parametric representation of your line. So this is a circle, so we all know a circle centered at the origin has radius r. Will have its parametric representation is x equals r cosine t, y equals r sine t, where r is the radius. So this particular guy, x is just going to be cosine t because the radius is 1, and y is just going to be sine t. And before I jump in, I might as well find out what dx and what dy are. So if x is cosine t, dx is the derivative of cosine t is minus sine t dt, and dy is going to be the derivative of sine t, which is cosine t, times dt. All right, and I'm going to take that parametric representation and plug it in to y dx minus x dy. Okay, and that's going to give me now, what's t ranging from? As I go around that circle, t is going to be ranging from 0 to 2 pi, absolutely. Where I see y, I take it out and I put sine t. Where I see dx, I take it out and I put in minus sine t. Notice I put parentheses around minus sine t because we're multiplying here. We're multiplying y times dx. Minus x, x is cosine t. And dy is cosine t dt. And so this is equal to the integral from 0 to 2 pi of minus sine squared t minus cosine squared t, and I'll just factor out the dt at the very end. And why did I do that? I'm not doing this integral separately and that integral separately because if sine squared plus cosine squared adds up to 1, then minus sine squared minus cosine squared is going to add up to minus 1, right? So this is equal to the integral of minus 1 dt as t goes from 0 to 2 pi. And so this is minus 1 t. Pop in 2 pi, you get minus 2 pi. Pop in 0, you get 0. And so we got minus 2 pi. Okay, by doing our line integral along that circle. Okay, so now let's see if we get the same answer if we do it using Green's theorem. Okay, and we will. Green's theorem says the integral over the curve of p dx plus q dy is equal to the integral over the surface of partial of q with respect to x minus partial of p with respect to y dA. Notice my region here is the circle of radius 1. So this one, let's see, I think I can do this in my head. Notice this is p and this is q. So this is equal to the integral over d of partial of q with respect to x is minus 1. Partial of p with respect to y is 1. Again, this is a negative 2 times the integral over my region of dA. And what is that? That's the area of the region. When your integrand is 1, or you don't even have a number there, it's 1. That's the area of the region. And what's my region? My region is that lovely little unit circle. A circle's area is pi times r squared. The radius is 1. And so we got minus 2 pi again, which is good. That shows me that Green's theorem is we've sort of justified it. If I take the area along the line, along the simple closed curve, or the integral over the region, using Green's theorem, I get the same answer. Okay, let's look at this one. Use Green's theorem to evaluate the line integral along the positively oriented curve of the triangle that goes from 0, 0 to 1, 3 to 0, 3. So first of all, I want to draw my region. And that's the hardest part, if you ask me, or the most important part. 0, 0 is right here. 1, 3, you're going over 1 and then up 3. 1, 2, 3, so that'd be around here. And then 0, 3 is right here. So we're going from here, that way, then this way, and then down. So notice the region that's enclosed by that is that one right there. Okay? So, popping this in, this is the integral along the curve of p dx plus q dy. Notice this integral, these are polynomials. So the partials are defined and are continuous along the curve, but also the entire region. Okay? So therefore, Green's theorem says that this integral is equal to the integral over the region of the partial of q with respect to x minus the partial of p with respect to y dA. So we just have to keep our head straight. Partial of q with respect to x is what? 4y cubed. Partial of p with respect to y is 2. Bring down a 2, and we get 2x squared y. And then we're going to go dA. Okay, and we got to decide how we're going to do it. Okay, now I think I can just slide this up here. So this is going to equal the integral over d of 4y cubed minus 2x squared y. And we can go to y dx or dx dy. I think I'll go dy dx. So I need an equation for this line right here. Well, that slope is change in y is 3, change in x is 1, so it's 3 over 1. So it's going to be y equals mx plus b. Slope is 3, so it's 3x, but the y-intercept is 0, so it's just y equals 3x. And checking, putting in a 0 here, that point's on the line, yeah, it works. Putting a 1 for x, yeah, it works. So we're going to be integrating 4y cubed minus 2x squared y dy dx as y goes from, now take an arbitrary x and bring it perpendicular to the x-axis, and what is y ranging from? Y is ranging from 3x to 3. And then if I sum up all those strips going that way, the x's are ranging from 0 to 1. Okay? All right, and I don't think we need to go through and do this one, do you? I mean, the whole idea is setting them up. You go through and do that, and you'll get, it's a nasty fraction, 3/18 over 5. But I think at this point my students know how to do double integrals. Okay. Okay, otherwise you're like, fast forward, I don't want to listen to her. Okay? All right, let's do another one. By the way, let me ask you something. What if I did not want to go this way? Instead, I want to go clockwise. What if my curve, we'll call that C1 of p dx plus q dy. What if I go in the opposite direction? What if I change my direction? What would the integral equal then? Negative. It would just be a negative 3/18 over 5. Good job. Okay, let's do another one. Next one I want to look at, I want to talk about Green's theorem can be extended to regions that have holes. All right, now notice, my lab technician drew these, and it's not real smooth. When I looked at it, I was a little bit upset. I said, it's not beautifully smooth. She's got corners here, and I like my curves to be smooth. But notice, Green's theorem says C is a positively oriented, piecewise smooth, simple closed curve. Now, this region here, if you look at this region here, it's bounded by two curves, C1 and C2. You go, well, you want one simple closed curve, Mrs. Strocko. You have two curves there, and they're not even intersecting. So how can I transverse that curve? Well, let me show you how we're going to do it. And don't take notes. Just sit back and follow, all right? Let's start coming along here, all right, till we get to about here. And then what I'm going to do is I'm going to go this way. Okay? Then when I get here, notice, think of a little man, and he's walking along the edge. He wants to keep his left arm in the region. You with me? So which way is he going to go so that his left arm's in the region? Here's my little guy walking. He's going to go down, isn't he? He's going to walk this way. In fact, she has the arrows there already, so you already know. We'll walk around till we get there, and then when we get here, we're going to go back that way. Now, I really should have the two lines written right on top of each other, right on top of each other. Then I'm going to go up and around, Okay, and I could go all the way around, but instead, let's do it this way. Oh, he could go this way, all the way around, stop. Let's go this way. Okay, all the way around down. Okay, so we're going to go up to here, through to here, up to here, here, all the way around here, and then we can go all the way around up here to here, back through here, and all the way to here and down. And that way we've gone all the way around the edges. So I've just added two little pieces that I've cut, two little slices. Okay, now you go, will Green's theorem work? I'm wondering if I call C to be C1 union C2 union, I'll put the extras. All right, now notice the integral over the extras are going to cancel each other because one time you're going this way and the other time you're going that way. One time you're going this way, the other way you're going that way. So these guys cancel each other. So I don't really have to do my line integral over the extras. So my question is, I'm wondering, if I integrate over those two curves of p dx plus q dy, will that still equal the integral over that d, that shaded region, of partial of q with respect to x minus partial of p with respect to y dA? And the answer is yes. And let me just take a minute and show you why. Okay? Notice, let's call this shaded region up top as D1 and the shaded region down bottom is D2. All right? So I'm going to call this one little piece going here, around to here, and up. I'm going to call him C prime. And notice this other little piece that goes here, all the way around to here, down to here, I'll call that part of the curve C2. Now, I think you will agree that this top half, which I'm calling D1, that satisfies what Green's theorem says. We've got piecewise smooth curve, we've got a simple closed curve, it's a simple closed curve. Therefore, the integral over D1 of partial of q with respect to x minus partial of p with respect to y dA will equal the integral along C1 of p dx plus q dy. And I think you would also agree that if I I shouldn't call that C1, he was C prime, I apologize. C prime for the top guy. And also the double integral over the bottom guy, D2, of partial of q with respect to x minus partial of p with respect to y dA would equal the integral over C double prime of p dx plus q dy, because that's also a simple closed curve when you go like this, like that. Now if I add these two together, if I add region D1 with region D2, what do I get? D. And if I add C prime with C, I want to call him C double prime, the bottom guy, notice you have these two extra little pieces, but when you integrate over them, what happens to them? They cancel each other out. And so in reality, that's just the integral over C, which is the two curves. And so therefore, Green's theorem can be applied when you have a region that looks like this. But just notice the inside guy, you're integrating in a clockwise rotation. So let's apply it to this problem right here. Use Green's theorem to evaluate the line integral along the positively oriented curve where C is the boundary of the region between the circles x squared plus y squared equals 1 and x squared plus y squared equals 4. So the region that we want to integrate over is the region that's bounded by the circle whose radius is 1 and the circle whose radius is 2. So we want to integrate, if we wanted to do it as a line integral, we would go counterclockwise for the outside guy. Then we could take a slice and come in here and then go around this way and then come back here and do a slice back here and then come back and do a slice coming backwards and then continue going around here, slice back this way, and then all the way around. And as you can see, these two slices negate each other because they're going in the opposite direction. And what we just proved a few minutes ago the integral over that curve of p dx plus q dy is again equal to the integral over d of partial of q with respect to x minus partial of p with respect to y dA. Okay? Where d is this annulus, the region that's determined by those two circles. So using this, let's see, setting up this integral here, this is going to be the integral over d of, this is my p, this is my q. So I say, what's the partial of q with respect to x? All right? The partial of q with respect to x is 4x cubed plus the integral of that with respect to x is 4xy squared minus the partial of that with respect to y is 0. Okay? Everybody okay? All right, now what are we going to do? We've got to figure out what our region is. Now, how do you want to do this integration? We've got to set up our limits of integration, dA. What do you think?
Factor an x out? Factor an x out?
I can factor out an x. Okay, now if I factor out an x, in fact, why don't we factor out a 4x? We'll get x squared plus y squared. How do you want to do this integral? I think polars. Yeah, absolutely. Let's do polars. I'm going to redraw that region right here for us so I don't have to keep looking at it. It's a circle of center of radius 1 and another circle of radius 2, and we're just talking about this region that's in between. So if I do polars, where I see x, I replace it with r cosine theta. Where I see x squared plus y squared, I replace it with r squared. And where I see dA, I put r dr d theta. And so therefore, this integral here will become 4r cosine theta times r squared times r dr d theta, where what's r ranging from? From 1 to 2. And theta's ranging from 0 to 2 pi. All right, so cleaning this up a little bit, let's see. We have the inner integrals from 1 to 2 of 4r times r squared, 4r to the 4th, cosine theta dr. Just bring the cosine theta out front, and that gives us cosine theta times 4/5 r to the 5th. And we're going from 1 to 2, which is cosine theta 4/5 times 2 to the 5th is 32 minus 1. So it looks like I have cosine theta times 4/5 times 31, which is what, 124/5 cosine theta. Now I have to take that and put it into the inner integral. All right? So we're going to go, I'll put the 124/5 on the outside, integral from 0 to 2 pi of cosine theta d theta. That equals 124/5 sine theta. And look at this, we're going from 0 to 2 pi, so we have 124/5 times sine of 2 pi is 0, sine of 0 is 0. All that work to get a stinking 0. Okay? So therefore, the reason we included this one is that you can do it when you have a hole in your region. Okay? As long as the partials are defined and continuous over the entire region and the border. And as you can see here, my partials are just going to be exponentials and polynomials, so they're always continuous. Okay, let's look at this one. Use Green's theorem to evaluate the integral of f dot dr. I like this one because you see f dot dr and you go, what's that, Mrs. Strocko, f dot dr? That's the same thing as p dx plus q dy. When you see f dot dr, don't get disheartened, because notice your f is just like pi plus qj, right? And your dr is just dx times I plus dy times j. So when they write f dot dr, remember when you take dot product, that just means it's p dx plus q dy. So they're just saying the exact same integral. Okay? And Chris was a little cavalier about putting this, but all of these are going to be closed curves, so it'd be nice to put that little circle there just saying that you're going over a closed curve. Okay, now what's my region here? My region goes from 0, 0, 0, 0 to 2, I'll put 2, 6 right here. 0, 0 to 2, 6, and then from 0, 0 to 2, 6, and then from 2, 6 to 2, 0. 2, 0 is right here. So we're going down. And then from 2, 0 to that. Look at that orientation. When that guy's walking around, his right arm's going inside, isn't it? Okay? So the integral over this curve of p dx plus q dy is going to be the opposite of what we get with Green's theorem. Are you with me? Because Green's theorem is with Green's theorem, we would be having to go in this direction. Okay? Everybody with me? Because this orientation is not positive, it's negative. All right, so to do this, we want to get the integral over d of minus partial of q with respect to x plus partial of p with respect to y. And the reason we put that minus sign there is that this particular curve is not going in positive orientation, it's going in negative orientation. So let's see. My p here is y squared cosine x. So what's the partial of p with respect to y? 2y cosine x. And my q is 2y sine x. So my partial of q with respect to x is just 2y cosine x. Okay. Okay. Do I have that right? P, take the partial of p with respect to y, we get 2y cosine x. And q is, oh, you guys, you didn't holler. I left part of q out. I was thinking, oh, these guys are going to cancel. I'm done. The answer is 0. But no, we're not that lucky. It's x squared plus 2y sine x. So that partial is going to be, the partial of that with respect to x is 2x plus 2y sine x. Okay, so plugging that into here, we get, let's see, minus the partial of q with respect to x is minus 2x minus 2y sine x plus partial with respect, oh, not sine, that's cosine. Because we're taking the partial with respect to x. This is a cosine. And then we go plus partial of p with respect to y is 2y cosine x dA. So for that particular one, we're quite lucky that these guys cancel. So we're just integrating over minus 2x dy dx. And let's go back and look at the region. Okay, that's my region. Did anybody get me an equation for this line here? What's the equation? What's that slope of that line? Its slope is, your change in x is a positive 2, your change in y is a positive 6, so it's a slope of 3. So that's just going to be y equals 3x. So if I take an arbitrary x, and what is y ranging from? It's ranging from y equals 0 to y equals 3x. And if you add all those up, your x's are ranging from 0 to 2. Okay, and this is another one that's going to be a pretty easy one to do. I'm not going to finish it. Okay, let's finish it. Let's do the inner integral real quick. No, Mrs. Strocko, you did enough. Okay, the integral of minus 2xy is, minus 2x dy is minus 2xy, as y goes from 0 to 3x. So we'll have minus 2x, put a 3x in for y, and then when you put a 0 in, that just gives you 0. So we have minus 6x. And then we have to take the minus 6x, and that gives me what, minus 3x squared? And we're going from 0 to 2. Whoops, did I make a mistake? Where's my mistake?
2x times 3x.
2x times 3x is 6x squared. And so we're going to go 6x squared here. And this will give me what? X cubed. And divide by the 3 gives me a negative 2. And we're going from x equals 0 to x equals 2. And that gives me a negative 2 times 2 cubed is 8 minus a negative 2 times 0. And we get a minus 16. Okay, everybody okay? Okay, what else do we have to look at? Okay, looking at this one. This one, if you look at this, look how hideous your function f is. Your function f has a p equal to y minus the natural log of x squared plus y squared. And the q is equal to 2 arctan of y over x. Now notice this is the circle. X minus 2 squared plus y minus 3 squared equals 1. Let's look at that circle before we do anything else. That circle, x minus 2 squared plus y minus 3 squared equals 1. What's the center of that circle? Its center's 2, 3. What's its radius?
1.
Its radius is 1. If I drew that circle, 1, 2, 1, 2, 3. The center's at 2, 3. 2, 3. It has a radius of 1, so I can go to the up, down, right, down. That's what my circle looks like. Okay? Look at this function. This function is defined for everything. This is defined for everything as long as x and y are not equal to 0. Because you can't take a log of a negative and you can't take a log of 0. So if I had x and y both being 0, this would be undefined. But that's not a problem here in that region because the origin's down here. Arctan, I can take the arctan of anything, but what can x be? 0. Well, x equals 0 is the x-axis. X equals 0, yeah, is the y-axis. And we're not that region's not intersecting the y-axis either. So this function's well defined. And when I take my derivatives, we'll see that my partials are also defined on that region. So we can apply Green's theorem. Now let's see. The partial of p with respect to y is the partial, if we take the derivative of y, we get a 1, minus the partial of this with respect to y, derivative of log u is 1 over u, times the derivative of u, and the partial of x squared plus y squared with respect to y is 2y. Now, this is q, so the partial of q with respect to x is, what's the derivative of arctan? Remember when you have y equals arctan, what was the derivative? Remember what the derivative of arctan u was? 1 over 1 plus u squared, and then don't forget to multiply times whatever the derivative of u is if you're going with respect to x. So if this is partial with respect to x, it's going to be 2 times 1 over, this is my u, 1 plus y over x squared, times, we have to figure out what's the partial with respect to x of y over x. You with me? Sort of running out of paper here, so let me put it here. I've got to multiply it times the partial with respect to x of y over x. I think I'd prefer to write that as partial with respect to x of y x to the minus 1. And so that's going to be y times, bring down your minus 1, leave this alone, decrease your exponent by 1. So it's going to be minus 1 over x squared. Are we all okay with that? Minus y all over x squared. And I think I'm going to multiply this out. This gives me 2 times 1 times minus y is minus 2y over, now notice this is this times this, so 1 times x squared is x squared. And this is y squared over x squared times x squared gives me y squared. Okay, so Green's theorem says this hideous integral of p dx plus q dy over that curve that we just drew, that circle, is going to equal, my integral is going to equal the double integral over my region of partial of q with respect to y, with respect to x, minus partial of p with respect to y dA. And a few minutes ago I got what these partials are. So this equals And you're like, oh, this is awful. But let's look what we have. Partial of q with respect to x is minus 2y over x squared plus y squared minus partial p with respect to y is 1 minus 2y over x squared plus y squared. What's the good news here? Something cancels, huh? Because you have minus 2y over x squared plus y squared minus 1, but then minus a minus is a plus. These guys cancel each other because it's minus this plus that. So we just have the integral over d of minus 1 dA. But my area is a circle. It's the area of a circle, right? And what's the area of my circle? The area of that circle is pi r squared. And that's going to give me pi times 1 squared, which is pi. So we'll have a negative 1 times my area of my circle, which is minus 1 times pi, which is minus pi. Minus pi. Okay, one more thing I want to talk about, and this is sort of cool. If you have a region, there are 3 integrals that will always give you the area. Look at this. Here's my curve, okay? I'm going along my curve. I'll call that C, and then in the region inside, we will call D. Notice, we could write this curve as the integral along the curve of 0 dx plus x dy. Now remember, Green's theorem says, we'll just put that right here, it says that the integral along the curve of p dx plus q dy is equal to the integral over the area of partial of q with respect to x minus partial of p with respect to y dA. Now, keeping that in mind, notice this is my p and this is my q. So this is equal to the integral over the area of partial of q with respect to x is 1, partial of p with respect to y is 0, dA. This gives me 1 dA, gives me the area of the region. Okay? I also could take this integral. Notice this integral, I could write the integral along the curve of minus y dx plus 0 dy. Green's theorem says that would be the area over the region of D of partial of q with respect to x. Well, q is 0. Minus the partial of this with respect to y is a negative 1 dA. And you get the integral over the region of 1 dA, which again is the area of the region. So this integral, this line integral along the curve, would give me the region. Look at this one. This one I'm going to write as the integral along the curve of minus 1/2 y dx plus 1/2 x dy. Applying Green's theorem again, this is the integral over the region of partial of q with respect to x is 1/2 minus partial p with respect to y is minus 1/2. Look what I get again. I get the integral over d of 1 dA, which is the area of the region. So in summary, using Green's theorem, all 3 of these line integrals over these simple closed curves will give us the area of the region that's inside them. Okay? So I would put those down. I think they're nice things to remember. But using Green's theorem, we just proved that the integral of each of these gives me the area of the region. So in closing, the last problem that I want to do today is I want to find the area of this ellipse. X squared over 16 plus y squared over 25 equals 1. And the way I'm going to do it is, notice this ellipse. Can anybody tell me in drawing this ellipse? If you let y be 0, what's x? Plus or minus 4? And if I let x be 0, y is plus or minus 25? Plus or minus 5, excuse me. This ellipse looks like this. And what I want to do is I want to do a line integral along this edge of the ellipse of the integral along the curve of x dy. because that was the very first one that we used Green's theorem to show that it gives you, indeed gives you the area in that region. But first, we have to come up with a parametric representation for that curve, for the ellipse. Hint, 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 hint. Here's my hint. I have the curve x squared over 16 plus y squared over 25 equals 1. Now I know cosine squared plus sine squared is equal to 1. I'm going to write x squared over 16 as x over 4 squared, and I'm going to write y squared over 25 as y over 5 squared. So if I let x over 4 be cosine, and if I let y over 5 be sine, do you see I get x squared, x over 4 squared? So my parametric representation is x equals 4 cosine t, y equals 5 sine t. Okay, you probably remember us doing that back in chapter 11 when we did parametrics. So this is the and notice how nice this is. This isn't that awful. Notice this. Just look at this for a second, please, for a second. Notice as t ranges from 0 to 2 pi, notice since you have 4 cosine, that's making your x-coordinate go from 4 to minus 4. You with me? And as sines going from the whole rotation, your y-coordinate's going from 5 to minus 5, and that's how you're getting the ellipse. But now that I have my parametric representation, we want to do this curve, so let's just write this down. We have x is 4 cosine t, y equals 5 sine t. What's t ranging from? From what to go all the way around that ellipse? 0 to 2 pi. And the integral that we want to do is the integral along that curve of x dy. So I'm going to let my parametric representations take care of things for me. So for x, I'm going to replace it with 4 cosine t. What am I going to replace dy with? Well, if y is 5 sine t, what does dy equal? It's equal to dy dt times dt, and the derivative of 5 sine t is 5 cosine t. Don't forget the dt. And what's t ranging from? From 0 to 2 pi. So we have the integral of 20 of cosine squared t dt. And how do we integrate a cosine squared? We replace it with 1 plus cosine 2t over 2. We used that many times in the last chapter. It should have stuck by now. All right, so I can divide 2 into 20 and get 10. And now I have to do that derivative, or that antiderivative, excuse me. The integral of 1 dt is t. And now I need to have a function whose derivative is cosine 2t. Well, let's try sine 2t. But if I take the derivative of sine 2t, I get cosine 2t times 2. So I'll need a 2 on the bottom for them to cancel. You with me? And then we're going to go from t equals 0 to t equals 2 pi. And this is going to give me 10 times, popping into 2 pi, plus sine 4 pi over 2, minus 0 plus sine of 0 over 2. But let's see, this is 0, that's 0, that's 0. So we just have 2 pi times 10, which is 20 pi. So we just figured out that the area inside that ellipse is 20 times pi. Okay. Well, I think we did enough for today. What I would like you to do for next time is read pages 1119 to 1124. And then on page 1125, I'd like you to do numbers 1, 3, 7 through 17, the odds. Okay, and I'll see you next time. Bye-bye.